There's a point though about Mike that I could mention in regard to risk. You know, he's done a lot of things that look risky to people who don't have his talent or don't do that kind of thing, rock climbing and so on. But my impression is, of all these things he's done, all these stories we hear about rock climbing, including some of the ones I've been on, is that he's always well within his capabilities. He's a prudent rock climber, actually. In fact, if you're here Friday afternoon when we discuss the incidents in late August 1981 when he announced the proof of the four-dimensional Poincare conjecture and so on, that was far more risky than I've ever seen him do anything or heard of him doing things when he was climbing. So I just wanted to clear that up. So our next speaker is Janka Likili. And there's his title.
Thank you. It's great to be here, and thank you for the invitation. Okay, so I'm going to talk about Fukaya theory of the punctured Torus, and this is going to and this is going to work with Team Torus. So let me start. So T2 is the closed torus. On this one we just pick an area form and pick a point, and punctured torus is the complement of the point. And the syntactic form that we have here is an exact syntactic form. And I'm going to report two theorems which are related. So the first theorem that I'm going to state, which is our joint work, is the Fukaya category, which I'll try to properly define, generated by A and B curve, is not formless. Where A and B curves is the obvious curves that you would think on a punctured torus. So this is the punctured torus. This is my puncture. So C. And this is A. This is B. So, and the second theorem, which
is not what?
Is not formal. I'll explain exactly what it means. So, sorry?
You might want to write a little larger. It's very hard to read that.
Okay, so this is the most important form, not formal. And basically what it means is that you have to work with infinity structures. So that's what I'm going to explain. And theorem 2, which follows from a good understanding of this, is the verification of homological mirror symmetry for the punctured torus. So let's see this. So and this means, okay, so I'm sorry, this is not important, right? This is so the big thing is this. So the Fukaya category of the punctured torus, I have to take complexes, and I have to take the Karugi completion as in my spoke. This is quasi-isomorphic to perfect complexes on a nodal elliptic curve. So C is so these are the statements, and the goal is first to explain why we started to study this, but our initial intention was to study Hegarth gnomology and low-dimensional topology. So first I'll explain why we got into this business, and second, my task is to make statements as understandable as possible. All right, so motivation. Um, also at Zalo, construct the Tegar thermal here. And in range, let's say half of the tree manifold, or actually the closed oriented tree manifold. And our motivation was to expand this absurd theory to three manifolds with boundary. So with non-empty boundary. And the simplest case is when the boundary is close. So let me take a sketch what Hegar's thermology is. So we have a tree manifold, we have a Hegar's splitting, we have a Morse function, we have the alpha curves coming from the stable and unstable manifold of these critical points and the wave curves. And there is a base point. So Hegar's thermology, the simplest version of this tree manifold Y is the Lagrangian thermology of Hegar tori inside the symmetric product of the Hegar surface, where you take out the divisors associated to a base point. And so Lagrangian thermology is generated, so this is generated by intersection points of T alpha and T beta. This is T alpha. And one counts homomorphic Torus as a differential. So this is maybe the first low dimensional topology conference that Hegar's thermology was not defined until the first day. So okay, so this is the usual picture, and well, what we want to do is to do the same for a tree manifold of this form. And so this is still work in progress, but part of the work that's needed is to understand the Fukaya theory of the punctured torus. And the reason is the natural thing that you would associate to such a tree manifold is a module. So, and an infinity module. Over the Fukaya category of the punctured torus. So the Fukaya category is associated to this boundary, and to the tree manifold you get a modulo out of it. So, and until I define things, let me give you a quick way of thinking about these things. So this is just you can think that this is finite many objects, which are Lagrangians, and you can look up the algebra out of it. So let me say M1, Mk. And the algebra is just the home spaces. So these are the Fleur homology of Li, Rj. And this one is some immersed Lagrangian. And so what it means to be a module is that whenever I pick an object here, I can take the Floer complex. And y, what it does is to an object, it associates the Floer complex. And whenever you have a morphism, you can multiply that with anything here. So, yeah.
Let me ask for your notation from L1 to LJ was each of those curves on the torus.
Right, so I'll define what this is properly, but I'm just giving you a picture of what this a infinity module over some Fukaya categories. This is some explicit algebra, so you'll see that it will be six-dimensional algebra, and yeah, so the objects will be closed embedded curves, but actually I'll just leave two objects, so there will be A and B. Let me go on.
Is the torus the same as the boundary torus?
Yeah, that torus is the same as the boundary torus, and there is a base point, and I take out the base point.
Punctured?
Sorry?
The base point is related to the punctured?
The base point is related to punctured. Yeah, so whenever I have a picture like this, maybe I choose a Morse function that connects punctured to the maximum, or maximum, and then I take out that point.
Okay, you want to define capital H, F,
Yeah, so what I want to say is that this is not some magic, this is just some explicit algebra, and this is some immersed Lagrangian. That's what the picture should be.
This is independent of the choice of the syntactic structure, like the data choice.
Yes. So as I said, this is not the main focus of this talk, but the main difficulty here is to show that this construction does not depend on the choice of the Morse function. And that's the work in progress.
When you refer to inverse Lagrangian, you obviously that's like manifold.
Yeah, it's in T-naught. This one. It's the Torus. So again, let's not, sorry, maybe I should have brought up this feature. Let's not pay attention to this too much. I'm just trying to tell you that I want to study this. Okay. That's what I want to study. And this will be relevant later in this question. Yeah.
So the order for a model gives you this.
Yes, exactly. So yeah, this is an alternative approach to the border terminology. And yes, this would be, so this is, so the border terminology is so if I want to compare, it allows non-compact Lagrangians. And it only works for the hat terminology. So this allows only compact Lagrangians, and it will work for any version of the graph terminology. And there's a relation, but there are different categorifications in some sense. Right. So, and the key point of this construction is that if I have two manifolds with boundary, then the modules that you get, you can transfer them. So let's say the boundary is a torus, then you can transfer them over this algebra, and what you get is the chain complex for the closed triangle. So okay. So I'm going much slower than I want. So the main point now is that Lagrangian, but I want them to be exact. So that means that the integral of theta over L is 0. So this is exact Lagrangian. And when you impose this condition, a simple fact is every monotopic class of curves, those curves, is realized by an exact Lagrangian. And uniquely after Newton isotopy. So it's as complicated as simple as this. Right? The objects are this. So the morphisms. Well, you have. So let me start with. So let me start with the simplest one. So the morphism between two Lagrangians is just a third chain complex. So this is. So this, you first perturb the first one by some Hamiltonian perturbation in the case where they are not transverse, and it's generated by these intersections. Okay. And there's the usual Floer differential. So the Floer differential counts homomorphic curves. Just like there. So up to now, we are in a very simple situation. So such a simple situation that we don't want to even, claim anything about it. But it gets more complicated when you want to define higher products.
So sorry, did you?
Yeah.
That's your the morphisms are the chain groups.
Yeah, the morphisms are just the intersection points, and the only thing that you might be careful about is this perturbation. So for each Lagrangian, for each pair of Lagrangians, you choose a perturbation such that they intersect transversely. And this you fixed. So now you want to do the same, right? You want to count. So the higher products will count these polygons. And so in K will be maps from the morphism spaces. So it will count holomorphic polygons with, you feed these intersection points to the corners. But the point is, now we have to arrange everything to be transverse, right? So these curves can be all the same curve. I have to choose Hamiltonian perturbations for each such configuration. And that's hardly non-trivial. And it was proven by Paul Zeidel in his book that you can do this consistent choice of perturbations. So when I say consistent, it means that so I got up to mu1 there, and I have to now pass to the next level, and when I'm passing to the next level, I have to keep my previous perturbations. And yes, so this is done. So we take our time, and this is what I'm with. But the main problem is that how to count these UK. So there's this horrendous schemes of perturbations Hamiltonian perturbation, then my category will be quasi-equivalent to the previous one. So I'm always allowed to choose Hamiltonian perturbations, but I need to make them I need to choose them consistently. For example, one of the things that the A infinity relations come from the generations of one-dimensional moduli spaces, right? If I try to count one-dimensional moduli space like that, then if I degenerate, I can degenerate them along this line, this line, or this line. So I'll get counts like this at the boundary of this moduli space. You get things like this, and so on. So there's going to be 4 of them. And this is basically what it means that these counts satisfy the infinity relation. But now, in order to satisfy this infinity relation, all the perturbations that I use to count this triangle, all the perturbations that I use to count this rectangle, whenever it's degenerated, it should reduce to my previous perturbations. So that's the technical part of this story, and that's why one can't compute this. So, all right. So how to characterize this algebra, this category?
Why did you say before you had only finitely many objects?
Yeah. So I'm getting there. So. Characterize. So, and the meaning of the word characterize will be obvious once I write it. So the first step to do is find generating set. So this means it's a sub-algebra, subcategory. So I want to find this A, which will be subcategory of the Fukaya category I'm studying, such that after algebraic operations, which means direct sum, shift, or taking cones. So let's call this twisted complexes. So I start from objects here, and I form these complexes, and I can take direct sums of things, say, shift them, or take cones. So this is this. Then what I get is a quasi-equivalent to the same operations applied to objects in here. So this is, I don't know how to, so naively this is just picking some bases, right? And these complexes are all I care about. They have all the information about the modules or Fukaya category and so on. So there's one more operation that Freedman mentioned, which is this idempotent completion. And in that case, I could apply it here, which means I allow to take direct summands of my objects. So this man explained it very well, so I'm not going to discuss it further. So
The homomorphisms you choose, you take a full subcategory.
yes, it's going to be a full subcategory such that this is solved. Okay, and we are in a very good situation because we are working on this extremely simple symplectic manifold, the full subcategory that I'm going to take consists of this A and B. So it's easy, this is very easy to prove that the subcategory generated by A and B is a generating set for the full. So, and the reason, there's an obvious geometric reason for this, means that, you know, what does it mean to take cones? To take cones means to resolve the singularity. Okay. So for example, if I want to get any other curve, I can take the cone of this morphism to get to this curve. And if I want to get other slopes, then I just take many copies of this curve and many cones and so on. So this is the easy part.
So this is cone?
Cone is homological algebra, right? So
Yes, I don't see the relation between the homological algebra and cone and resolving singularity.
Well, I can explain it like this. Think about the surgery exact triangle in Hegel terminology. So whenever you have two curves and the third one is obtained by the cone of it, which is resolved, then they fit into an exact triangle. So this is a very, very basic case of Seidel's exact triangle. Okay, so therefore, we reduced to study, you know, I started from this abstract, which may not be abstract because we know all the curves, this category, and I took this small subcategory, and since it's a generating set, we reduced to study to that. So it's, now, the point is to understand this. I don't know if this is the right notation, but so understand this one. So at level of objects, it's obvious. At the level of differential and so that having some obvious observations, right? This is A and this is B. So what's the algebra that I think about out of this? The algebra is, so it has four terms. Remember, I told you at the beginning that you take every possible combination of the objects in your category. So, and this is just, so this has two generators. This is just the homology of the circle. This is the homology of the circle. And these intersect at two, each, so A and B intersect at one point, so there's only one generator for each of them. And I decorated things with 1 or 0 that refers to the gradient, so, which I don't want to discuss. All right, so at the level of, you know, this is the basis of the algebra, and the product is also easy. So here's a cheating way of describing the product. So I perturb my curves A and B, and now I look for triangles. So here's one triangle that corresponds to, so like enable these things. If I set things properly, this will be 0, E1, this will be F0, F1, and this is either U or V, depending on whether you consider the point as a intersection of A and B or B and A. So, and this triangle here corresponds to U1 times V0 is equal to E1. And there's sort of the other one, which is V0 times V1 is equal to F1. So the reason this is cheating is because I perturb my curves, and I still look at holomorphic curves on the picture, right? So in order to, so when you perturb your curves, your holomorphic curve equation changes. So I have an explicit algebra that I cooked out of my punctured torus. And now the question is whether there are higher products. So remember, this A is not the invariant of the punctured torus, but this complex is. This one is the invariant that I'm after. So this is sort of what you might call the heart of the subset. And in order to figure out that one, I have to figure out the higher products. So mu k will be so there will be maps from A tensor K to A. And so there is some explicit count of holomorphic curves that I need that in order to determine these higher products. So here's the technical point that comes up. So as you look at this picture, this A and B, you would not imagine that there is any higher products, right? This is sort of a trivial picture. So you would not think that there is any rectangles, any holomorphic rectangles mapping to there, or any pentagons mapping to there, and so on. So you would think that what we figured out from the cohomology is everything. And my claim is that there is non-trivial holomorphic curves mapping exactly to this point. And the moduli spaces are not regular. And since they are not regular, we don't know how to count them. So but my claim is that there is non-trivial contributions. So this is where the technicalities of the Fukaya comes in. And how do I justify my claim, right? So how do I figure out these things? And in fact, how do I figure out infinite, so there's infinite limit maps, right? So how do I figure out all of them? Because that's what I need to get this invariant. So the solution that we came up with is algebraic. Since top is not there, I can use this, right? So the way to figure out what this category is, let's consider the moduli space of pairs where B is an infinity algebra such and I is an explicit isomorphism within its homology and my given algebra. So I wrote A or A. Let me stick into. So this A2 I know is the homology of the infinite category that I'm after, right? And so the thing that I'm looking for is in this moduli space. And so I want to figure out which point it is and what's this moduli space. Any questions? So this is an isomorphism. So how do I do this? Well, there is something called deformation theory. Which in this very easy terms will allow me to understand the tangent space to this moduli space that I'm after. So there's an obvious element here, which is the formal one. So the algebra itself higher products 0, right? This is an element there. And I want to look at the time space there. So this is actually some Punctured cohomology group. So this is the Punctured cohomology of the algebra itself. So maybe I'll put R at 2 minus R. So these are some gradients.
Sorry, I
Yeah.
have a question. Are these eyes, what kind of maps are they?
They are
Just linear maps?
they're just isomorphisms from this is some these two are not associative algebras, and this is an isomorphism of associative algebras. All right, so this is the Punctured cohomology, and this is where we did something real. We computed this group.
So what's the issue associated? I thought there's a new theory.
Sorry, did I say? I'm sorry. I want to say anything. No. On the cohomology level, it's associative. So this is
On the other side, what is A2?
A2 is just the algebra, right? So A2 is the algebra where I'm trying to figure out the higher products.
But why is it associated?
Because it's the cohomology of the. So.
Is there different A's here?
It's not anything structured. No, the point is that the mu2 product is associated automotively at the chain level, but it's associated on the cohomology. So now I'm just so I passed the cohomology, and I'm trying to figure out how it works.
So
Hmm?
A2 has
That's right.
But they're not.
So they're actually higher massive products. That's what they're doing.
So is one computer or some definition of module space?
It's what?
Screw down is like definition.
That's the definition, yeah. It's a set. I don't, for now, I don't consider any structure. It's a set. It's the set of,
What is it said?
huh?
It's not a set.
What do you mean it's not a set?
You told me I'm used to something, so it's
Yeah,
ridiculous.
but I was wondering about a cool.
Oh, yeah, should I, yeah. It's up to quasi-groups. Okay, so this Punctured cohomology computation. So so the Punctured cohomology is some explicit text, right? And this X group you can compute by finding an explicit resolution of A2, and which better be not the bar resolution so that you can figure out it in a complete sense, right? And there is a resolution of this A2 algebra, a periodic resolution, periodic resolution. So, and the tricky thing is that you have to figure out the signs completely. So if you make any sign mistake, then everything is, like you lose everything. So first of all, so if I have time, I'll discuss this, that the Fukaya category over mod 2 is different than the Fukaya category over any characteristic field, or any field where the characteristic is 0. So let's stick to characteristic 0. The characteristic of base field is 0. And let me tell you the relevant column of this computation. So this is R. So let me call this S. This is S. I know all the parts of this, but the relevant code is this one. So the reason that this is relevant is the maps MUK are cochains in this, which fit into this column. So, and this is where mu6 would lie, and this is where mu8 would lie. Now muk is just that map, right? And alright, so what does this computation tell us? So it tells me that, so these are so like mu3, mu4 would lie here, mu5 would lie here. Since these are 0, the mu3, mu4, and mu5 are irrelevant. So I should not have bothered to compute it at all, because I can always find some gauge transformation. So this is equivalence, right? To trivialize mu3, mu4, and mu5. So I can assume that these are already 0. I tried very hard to compute mu3 from this picture by cheating, right? Because those perturbations are not allowed. So, and you get into trouble. So if you can compute something, but you can't prove that's the right thing, and in order to compute mu4, it's even much more messy. But the point is, these are not needed. So you do not need to compute these things. And next question is, what about mu6? The class of mu6. Is it trivial or not? And the point is, sorry, I should have said this, it's 0 from now on. The point is, if mu6 and mu8 are also 0, now that means that my infinity algebra is quasi-equivalent to the homology to its homology. So it would be formal. But the thing that we proved is mu6 is non-zero. The theorem is mu6 is non-zero. And that means that there is some syndrome that we can't see. But it contributes to the infinity algebra. So and the way we prove this is by looking at the DG model of this. So let me write it somewhere.
So why did you say it's cheating to actually draw the pictures?
Because you make infinitely choice of Hamiltonian perturbations, and so first of all, now your homomorphic curve equation is not homomorphic curve equation anymore. It is Hamiltonian perturbations. So you can't just say that you see it on the picture. But also, you don't. So that's one very extremely crucial problem. But another problem is, I don't know if I draw those pictures, I don't know if those pictures is a consistent perturbation. So since
So even on this very small algebra, we have just A and D.
yeah,
You can actually do the
Yeah.
consistent perturbations.
now there is no way, and the reason that this is problem here is that the moduli spaces are not regular. So for example, for sport approach, one doesn't know how to do it.
Does consistent just mean all the Lagrangians are transversal to the other Lagrangians?
So consistent just means that, so in order to compute mu k, I need to perturb k times the same Lagrangian. So suppose I want to compute mu k, where my input is always the same Flirt chain complexity.
What if this is what they call second category or something?
Sir?
Isn't an open net set of Lagrangians, aren't you just intersecting a countable number of open net sets in two circles per relation?
So, but you have to identify. So let me tell you. So let me tell you one obvious problem. So suppose I perturb like this, right? So So at some point I have to use something like this. It's the intersections of L prime and L2 prime. And I have to identify this in some canonical manner with CFL L prime, where I have to preserve all the infinity structure. So this is not obvious at all. All right, so
Yeah, that Kevin's answer was also relevant. He said that we have to think about the diagonal. This is that the transverse set themselves, which is not usual, not usual condition.
all right, so if you don't mind, let me continue. So the way we figured out this mu6 is, so there is a DG model for the Fukaya degree. So this is viewing T naught as a plumbing of two cotangent models of circles. So you can get a DG model and apply. So this is due to opposite, and apply homological perturbations. Which means kill the differential trait as, for higher products, and then do explicit gauge transformations to kill mu3, mu4, and mu5, and get a co-cycle for mu6, and then show that mu6 is not 0. So this way, so this is the proof of the first theorem. The second thing that I want to say is that M is actually just this K plus K. So it's a vector space. I mean, the reason that we were able to get this far is because the time and space to the moduli space already determines the moduli space because it's a linear space. So one can prove that the map from any A, so any A infinity structure, to its class mu6 and mu8 is a bijection. So, how much time do we have?
5 minutes.
Okay. So last part of this business is, so there is a C star action on A infinity structures. And what it does is it sends mu I, so an element of C star, T sends mu I to T to the I minus 2 mu I. This is for any A infinity structure, so it's a scale. And notice it doesn't change the products, right? So it's a C star action here. And the weights of this C star action on these two pieces is so it scales by T to the 4 here and T to the 6 here. So now think about where you saw those weights before. Until I get this. Now, so here is algebraic geometry. Okay, curves, right? The simplest version. So now I can look at the Walsh transform. So this is an elliptic curve. So it's the reason that I wrote algebraic geometry is now we have a different side, right? There's no symplectic probability. So now if I have, so let's look at this A and B. So the curve is given by quotient to the lattice, right? And if I scale this lattice, how does A and B change? So A and B change precisely like this, as we all know. So now it's the same weights. This is what triggered to think that these curves and their covariant sheaves actually are all elements in this moduli space. So there's the standard basis. So if I choose the spaces, then it gives me a canonical isomorphism with this algebra that I have been working on. So now you can think that the BG enhancement of this, which is an enhanced fancy word for saying that let's take a check cover and let's look at the differentials such that, So I have a BG algebra here. And that falls into my moduli space. And actually the map, so the map from Weierstrass curves, so this to AB, so is bijective. So that means that all the Weierstrass, so this moduli space is just spanned by this geometric, so by this Weierstrass terms. And if you take n equals to 0, which is the canonical element that we had here, the formal one, so that corresponds to the cost curve, this one. And if you take a and b such that they lie on discriminant, that corresponds to the normal curve. And that's what we proved. So the theorem is the perfect complexes. It just means that so this O and OP is a generated set for this perfect complexes. Is quasi-anthomorphic for C, the normal curve is to this. When the characteristic of K is not equal to 2. And it's harder in characteristic 2 and 3 because the Boxian commodity is harder, and also elliptic curves is harder because you don't get to this Weierstrass when you have more things. So this is work in progress, also covers the characteristic 2 and 3. In fact, this is an equivalence over Z. So that's the